So let's review chapters 9, 14, and 19 in preparation for exam 3. So this first question says the manager at ABC Retail is scheduling staff for the holidays. The information was gathered from the 2019 holiday season. So we have some data there in the table. The number of employees that were staffed at a single time and the sales per hour. So what we need to do is we need to determine the regression equation from the data. So that's going to be find our y hat. Then we need to find our coefficient of determination, that's r squared, and the sample correlation coefficient, and that's r. And then once we do A and B, then we can apply that information. So we can say, okay, if the manager schedules 20 employees, how much in sales should they expect? And how many employees should the manager schedule to make at least $300 in sales per hour? Right? So the whole reason why we do these regressions is to help us predict what's going to happen. So we're going to use this past data to predict future results. So we have this information over on the left. And when we're working through regression problems, we have this table, right? So the first step is to fill out either the x and the y. So what we need to do is we need to decide which of these variables is the x variable and which of these variables is the y variable. So what we're going to do is we're going to say that the number of employees staffed, that's our x. The sales per hour, that's our y. So we'll plug in all of our x's and all of our y's. So we plug those into this regression worksheet. Now you can see that the next few columns are for x minus x bar and y minus y bar. So we need to figure out what is x bar and what is y bar. So to find our x bar, we need to know the average of all of our x's, right? So we have our x's there in that first column. If we average all of those, we'll end up with 8.125. So that's going to be our x bar. And then we need to find the mean of all of our y's for y bar. That will be 213. So now that we have our x bar and our y bar, now we can start filling in the next couple columns. So the next one that we need to fill in is x minus x bar. So that's taking each individual x value that we have in that first column and subtracting 8.125. Right, so the first one would be 10 minus 8.125, then 12 minus 8.125. And so if we do that for the entire row, or the entire column, we'll end up with numbers like this. Right, so some are positive, some are negative, and that's okay. Then we move on to our next column. This is our y minus y bar column. So, pretty similar to what we just did, but now with our y values. So we have all of our y values there in the second column, and we want to subtract 213 from each of them. So 238 minus 213, 272 minus 213. And we get these values. And once again, some will be positive and some will be negative. Now, why did we do this work? Well, because we eventually are going to need the sum of our fifth column here. The column that's the x minus x bar times y minus y bar. We eventually have to sum up that column. So we had to do x minus x bar and y minus y bar individually to help us now be able to solve this piece. So your next column is just x minus x bar times y minus y bar. So for the first value, it would be 1.875 times 25. Then we would do 3.875 times 59. And we will end up with numbers like this. Now, once we have all of those figured out, we can move on to our x minus x bar squared. So we have all of our x minus x bars in our third column. We need to square those values. So 1.875 squared, 3.875 squared. And what's important here is that you should not have any negative values in this column, because by squaring a negative number, you get rid of the negative, right? So we had negative 0.125 in the third row. When we squared that, it became a positive 0.016. So we have our first 6 columns all filled out. The next column that we need is our y hat. So we've gotten to the point now to where we need to solve for our y hat. So the y hat, that's our regression line. That's the equation of the line. So they flipped it around a bit compared to what you probably learned in algebra, right? Here it's the y-intercept plus the slope times x. Instead of mx plus b, like you've probably heard a bunch, they just flipped those two variables. But it's the same idea. So we need to figure out b sub 0, which is our y-intercept, and b sub 1, which is our slope. We're going to first figure out our slope. So on your formula sheet, it tells you that the slope is the sum of x minus x bar times y minus y bar. Right? I said earlier that we were eventually going to have to sum up that column. And this is when we do it. So that'll be the numerator. And then we divide it by the sum of x minus x bar squared. So that's the sum of our next column. So if we sum up those columns, we'll get 908 divided by 64.875. Now, we divide those two, and we get a slope of 13.996. So that's going to be our slope for our regression line. Now, once we find our slope, we can plug that into the formula to find our y-intercept. So our y-intercept, that's b sub 0. To find that, we take our y bar, which we've found already, that's the 213, and we subtract the slope that we just found times x bar. That's our 8.125. So we plug in those numbers into our formula, and we find out that our y-intercept is 99.281.
Wait, how did you get the y-intercept again?
So for the y-intercept, we took our y bar that we found earlier, the 213, and we subtracted the slope that we just found times our x bar. So if we did our slope times our x bar, the 13.996 times 8.125, and then did 213 minus whatever we found there, that will give us our y-intercept. So now we can plug these values into our y hat. So our y hat equation is 99.281 plus 13.996x. So before we move on and continue with this worksheet, let's just think about what that formula, what that equation even means, right? So x was the number of employees staffed, and your y hat value would be your expected sales per hour. So for each additional employee that was staffed, you would be making an additional $13.99 an hour. But we also want to make sure that it makes sense if we were to say staff no one, right? So if we were to staff no employees, so x would be 0 in our y hat, we would still make $99 in sales per hour. So in this case, we can think of it as maybe online sales, right? Not every sale is an in-person sale. So that y hat formula, that y hat equation, still makes sense for our purposes. So now we can take that y hat and plug it into our worksheet. So what we need to do is we need to put each individual x value that we have over in the first column and plug that into our y hat. So we would have 99.281 plus 13.996 times 10, and that would get you that 239,243. Right? So we plug in each individual x value into that y hat equation. And that's how we get our values in our y hat column. So that y hat column, that's your expected sales per hour. So if we look at just that first row, if we were to staff 10 employees, based off of our y hat, we expected $239 in sales. We can notice that we actually had $238 in sales, based off of our y value that we had with that data. So we're pretty close there, right? So maybe our y hat is a good line. We're going to have to see how good of a fit it is later on. But based off of just that first test, we're not way off. So once we have our y hat, we can now move on to the next column, which is y hat minus y bar. So we have each of our y hats, and then again, we found our y bar earlier in the problem. That was that 213. So we take 239 minus 213, 267 minus 213, and we'll end up with these values. And again, it's okay that there's some negative ones in there. So we made this list, our y hat minus y bar, so that way we could now square it in our next column. Right? So we have our y hat minus y bar figured out. The next thing we need to do is y hat minus y bar squared. So we're squaring 26.243 and 54.235. Each of those values are getting squared. So you're going to end up with some big numbers here. But again, what's important is that we do not have any negative values. because whenever we square a number, a negative number, it becomes positive. Right? So negative 1.75 squared became positive 3.061. So once we have that list, then we can move on to our last column for this regression worksheet. And that's y minus y bar squared. So, a long time ago, we did our y minus y bar column, right? That's our fourth column on this worksheet. We now need to square each of those values. So we need to do 25 squared, 59 squared, negative 6 squared. And when we do that, once again, no negative values because we're squaring these numbers, and we get these values here for this last column. So the purpose of these last few columns here are to help us figure out the r squared and r. So, r squared, that's going to be the sum of y hat minus y bar squared divided by the sum of y minus y bar squared. So that's the sum of your last two lists. So if we sum up y minus y, or y hat minus y bar squared, we'll end up with 12,708. And if we sum up our last column, y minus y bar squared, we get 13,342. So to find our r squared, the coefficient of determination, we divide those two amounts and we get 0.9525. So it's great to be able to know how to calculate r squared, right? That's important. But what's really important is that you're able to apply this. You're able to say what this even means. So the way that we interpret r squared is that 95.25% of the change in sales per hour can be explained by a change in number of employees staffed. So a basic template for that is r squared is the percent of the change in y that can be explained by a change in x. So our goal for an r squared is to have it be as close to 100% as we can. So here 95%, that's pretty good for an r squared. If we were to be using this for truly for staffing purposes, like in the problem, I think we would be comfortable with trusting what this regression line would tell us. So if we can have it be as close to 1 as possible, we're in good shape. Now, after we find the r squared, the coefficient of determination, we can now find r. And r is the sample correlation coefficient. So, it's a little bit more than just the square root of r squared. We also need to put the sign of our slope in front of that number. So, if we take a look at this, at our y hat equation that we have down in the lower left, our slope is that 13.996. It's a positive number, so the r value that we will have here will be a positive number. So the sign of b sub 1 is positive, and then the square root of r squared. So r squared, we found that to be 0.9525. We take the square root of that, and we get 0.9760. So once again, it's great that we know how to calculate this, but calculating it means nothing if we don't know how to interpret what R means. So there was a slide late in the chapter 14 lecture that showed this chart of the interpretation of R. And that chart is going to help you when you interpret here. So since our R value is 0.97, we have a very strong positive, because the number is positive, linear relationship. Right? So that chart tells you that it's very strong based off of where your R value falls. The fact that our slope was positive tells us that it's positive. And then it's a linear relationship because we're just doing linear regressions. So now that we have all of this information, we can now finally start to ask or answer these questions. If the manager schedules 20 employees, how much in sales per hour should the manager expect to make? So remember, the number of employees were our X values, and our sales per hour, that was going to be our Y hat. So we plug in 20 for our X. And if we do this math, we can find that our Y hat, or our expected sales per hour, would be $379.20. So if we staff 20 employees, we expect to make just under $380 per hour. So that's one way that you can use this Y hat. Another way that you can use this Y hat equation is to flip it around. How many employees should the manager schedule to make at least $300 in sales per hour? Right? So if we have a sales goal, we need to figure out what we need to do to reach that sales goal. Right? So our goal is $300 per hour. So that gets plugged in for the Y hat. We're looking for how many employees should we schedule. So we leave X there. So we subtract that 99 from both sides. So we have 200.719 equals 13.996X. We divide each side by the slope, and we see that X equals 14.34. Now this is kind of similar to when you guys were trying to figure out the required sample size on the last exam, right? You can't schedule 14.34 employees. And if you were to schedule 14 employees, you wouldn't make enough in sales to hit that $300 mark. So you're going to have to round up and say that we need to schedule 15 employees, because that 15th employee is what pushes us over the $300 in sales per hour. So that's your regression stuff. So that was chapter 14. Make sure that you have that worksheet ready to go when you're working on these problems, because you're going to want to be able to fill out that worksheet as you go along. Now, going back to hypotheses testing. So we're going to have 3 different scenarios. We need to figure out what are the hypotheses, and then is it a one-tailed or two-tailed test? So our first scenario, it says a production line operation is designed to fill cartons with laundry detergent to a mean weight of 32 ounces. A sample of cartons is periodically selected and weighed to determine whether underfilling or overfilling is occurring. If the sample data leads to a conclusion of underfilling or overfilling, the production line will be shut down and adjusted. So we're going to need to figure out our null hypothesis and our alternative hypothesis. So here, whether we underfill or overfill, we're going to need to shut down. Right? So, if we think about the first 3 steps in that 7-step process, step number 1 was to write down the claim. Well, our claim here is that our mean weight is 32 ounces, right? So mu would equal 32. The second step is the opposite of the claim. So the opposite of your mean equaling 32 would be your mean not equaling 32. And then we need to figure out which one's the null and which one's the alternative. So your null hypothesis is always going to have the equality in it. So your null is either going to be equal to, greater than or equal to, or less than or equal to. Right? So in this case, since we're dealing with equal and not equal, our null and alternative will look like that. So if those are your null and alternative hypotheses, we now can figure out if it's a one-tailed or two-tailed test. Whenever it's equal and not equal, that is a two-tailed test. Now our next scenario. The Wall Street Journal reported that bachelor's degree recipients with majors in business received average starting salaries of $53,900 in 2012. The results for a sample of 100 business majors receiving a bachelor's degree in 2013 showed a mean starting salary of $55,144 with a sample standard deviation of 5,200. We need to test whether the mean starting salary for business majors increased. So, our claim is that our mu is greater than 53,900. Our claim is that it's increasing here. So that would be step number 1. Step number 2 is the alternative. So that's that the mu is less than or equal to 53,900. So now which one is the alternative? The alternative is greater than, because it does not have the equality. So our null is less than or equal to. So it's important to also recognize that we took the 53,900. We did not take the mean from the sample that they showed. We did not take that 55,000.
Why? Like, how do you know which one to choose?
So that 53,000 is our population mean. And so that's what we're going to deal with in the hypotheses. The 55,144, that's our sample mean. That was just the mean from that sample of 100. That's our X bar. And so that number will help later on when we'd have to calculate a test statistic. But here in the hypotheses, it's being based off of the population mean. So now we can try and figure out if it's a one or two-tailed test. So it's only going to be a two-tailed test if we had equal and not equal, like we did in the first part. So whenever we have greater than or less than, it's a one-tailed test. Now, why is it a right tail? So we take a look at the alternative hypothesis, and we see that that sign is pointing to the right. So that's what tells us, that's our hint that it's a right-tailed test. So now our last scenario here. Because of high production time and costs, a director of manufacturing must convince management that a proposed manufacturing method reduces costs before the new method can be implemented. The current production method operates with a mean cost of $220 per hour. A research study will measure the cost of the new method over a sample production period. So we need to once again figure out our null and alternative hypotheses. So we want to see if our new method is going to decrease the cost, right? So our claim is that mu is less than our cost of $220 per hour. So the opposite of that claim is that our mu is greater than or equal to $220. Right? So since we wanted to show that it's reducing our cost, that was our claim. So which ones are null and which ones are alternative? Well, the null is going to have the equality. The alternative is not. So the alternative is just less than 220. The null is greater than or equal to 220. Now, one-tailed or two-tailed, and then is it a right or left tail? So we know that it's just a one-tailed test, right? Because we have greater than and less than. That tells us that it's one tail. What tells us if it's a right or a left-tailed test is the way that the sign is pointing in the alternative hypothesis. So that sign is pointing to the left, so it's a left-tailed test. So we've sort of walked through the first 3 steps in that 7-step process for doing a hypothesis test. But let's talk about all 7 steps. Right? So we're first going to take a look at the critical value approach, right? Because we have the critical value approach and then we have the p-value approach. So let's first just take a look at the critical value approach. Step number 1, write down the claim, right? Just like what we were doing in that last problem. Step number 2, write down the opposite of the claim, right? So, for example, that last problem that we did, the claim was mu is less than 220. So the opposite was that mu is greater than or equal to 220. So that's steps 1 and 2. Step 3, figure out which one's the null hypothesis and which one's the alternative hypothesis. And once again, the null has the equality. So equal to, greater than or equal to, and less than or equal to. That's what will be showing up in the null hypothesis. Step number 4, that's the easiest one. That's just what's your alpha? What's your level of significance? Right? So a problem might say, alpha is 0.05. So step number 4, we just write down alpha equals 0.05. Step number 5, this is your test statistic. So this is when you find a z-score or a t-score based off of sample data. So in order to use a z-score, you need to first be able to prove it. Right? So that's your n is greater than or equal to 30 and sigma is given. N is greater than 100. Right? We need those proofs that we learned about previously to be able to use a z-score as our test statistic. If we can't prove, then that's when we move on and we use a t-score. So that's step 5, is we prove whether or not we can use a z-score, and then we calculate either that z-score or that t-score. And that's going to be called our test statistic. Step 6 is to determine the critical z-score, or the critical t-score if you were using t-scores. And so to do that, you need your alpha and your tail. So you draw a bell curve, right? And let's say in this case, alpha is 0.05. It's a one-tailed test. Let's say it's a left-tailed test for our scenario here. So we go over to the left side of our bell curve and we draw a line. That's going to start what we'll call the rejection region. So anything in that tail, in that left tail, is the rejection region. That rejection region starts at our critical z-score. So to find that critical z-score, the area in that rejection region is your alpha. So the critical z-score in this case, since our alpha is 0.05, would be negative 1.645. Right? Because that's going to be the z-score that has an area to the left of 0.05. Now, step 7 is to compare your test statistic to your critical z-score. And if the test statistic falls within the rejection zone, the rejection region, then we reject the null hypothesis. If it does not fall within the rejection zone, we do not reject the null hypothesis. So remember, we never accept the null hypothesis. We either reject or do not reject. So that's the critical value approach. We also have the p-value approach. And what's nice about these two different approaches is the first 5 steps are exactly the same. These approaches break off at step number 6. So in the p-value approach, you still write down your claim. You still write down the opposite of the claim. You still determine which is the null hypothesis and which is the alternative hypothesis. You still write down your alpha, your level of significance. And then you still find your test statistic the same sort of way. You still have to prove for a z-score, or you just use a t-score. So those first 5 steps, exactly the same. Step 6, slightly different. So step 6, we use that test statistic that we calculated in step 5 to find the p-value. The p-value, that is just a term for the area in the tail, right? So you found your test statistic to be negative 1.80, let's say. So we draw that on the bell curve, and we want to find that area in the tail. So we take a look at our z-score table, and we look up negative 1.80, and we find that area. And that area becomes your p-value. So once we found our p-value in step 6, we then use that p-value to figure out if we need to reject or not reject the null hypothesis. So the rule that we have here is that if the p-value is less than or equal to alpha, you reject the null hypothesis. So if the p-value was greater than alpha, we would not reject. Now, on an exam, she might want you to use both the p-value approach and the critical value approach, just to make sure that you know both approaches. But your conclusion from step 7, whether to reject or not reject, is going to be the same under each approach. They're just two different ways to get to that same final answer. So those are your 7 steps for performing a hypothesis test. So that's past 2 questions have been about chapter 9. So now let's do a question about the most recent chapter, chapter 19, right, with quality control. So this question says, a company has collected 15 samples of data with 20 observations each. If X bar bar, which is the mean of the means, is 18.75, and R bar, which is the mean of the ranges, is 6.5, compute the upper and lower control limits for the X bar and R charts for the process. So before we start figuring out the upper and lower control limits, let's first just figure out our variables. So we already know X bar bar and R bar. Those were given to us. Now, this next part, this is where you'll get tripped up in this chapter. Figuring out the difference between K and N. K is your number of samples, and N, just like it has all semester long, N is your sample size. So N is how many observations in each sample. K is how many samples are there. Right? So, in this case, we were told we had 15 samples. And in each sample, we had 20 observations. Right? So you can think of it as 15 different days. And each day, you took 20 observations. You took 20 pieces of data from each day. Now, why is this so important? Well, we'll see later on when we're computing our upper and lower control limits, we need to know the difference between K and N, so then that way we can figure out our constants in our formulas. So, we need to first do an X bar chart. So, on our formula sheet, it'll tell us that the upper and lower control limits are X bar bar plus and minus A2 R bar. So the upper control limit will be when we add those together, and the lower control limit will be when we subtract. We know X bar bar, and we know R bar. So we can plug those values into our formulas. Now A2 is going to come from this chart in the back of your z-score table chart. So we have our A2 column and we have a bunch of numbers. How do we know which one to choose? That's based off of your sample size. So this is where knowing the difference between K and N is really important. So our N was 20, so we're going to use the A2 of 0.180. So we plug that in into our upper and lower control limits. We do the math, and we see that our upper control limit is 19.92, and our lower control limit is 17.58. So, what does that mean? Well, we had all of these 15 different samples, right? If all 15 samples, if each of their sample means were between 17.58 and 19.92, we would be in control. If one of the 15 sample means were outside of our limits, it was either less than our lower limit or greater than our upper limit, then we would be out of control and we'd have to readjust production or whatever our situation would entail. So we need all of our X bars to fall within our upper and lower control limits to be in control. If one of them falls outside of those limits, we are out of control. So now we can do an R chart. In R chart, the upper control limit is R bar times D4, and the lower control limit is R bar times D3. So we take a look back at this table again for our factors. Once again, we need to know that our N is 20. So we go down to N is 20, and we can see that our D3 and our D4 are given to us there. So we plug those values into our formulas. So our upper control limit, 6.5 times 1.585. And our lower control limit, 6.5 times 0.415. So we multiply those out, and we can find out that our upper control limit is 10.3025, and our lower control limit is 2.6975. So what does this mean? This means that all of our ranges, each sample's range, has to fall within our upper and lower control limits. Any sample with a range less than 2.6975 or greater than 10.3025, we are out of control.